Hello everyone and welcome to the channel. This is a revision video for design of machine elements. In this video we are only going to do theory questions and no numericals. There are very few theory questions but they were asked before in exam, so I think that they should be covered. Moreover, first we will do the unit 2 theory questions and then we'll go to the unit 1 theory questions. So keep watching the video, like, share and subscribe if you still haven't. Let's go to our first question. So first we are going to see the definition of torsional rigidity. This came in semester exam in August 2014. So torsional rigidity is defined as the torque required to produce a torsional deflection or angle of twist of 1 radian in the shaft. Similarly, lateral rigidity is the lateral force required to produce a lateral deflection of 1 unit. So the definitions are very easy and they are kind of same. For torsional rigidity it's the torque, for lateral rigidity it's the lateral force to make a difference or to produce. For torque it's torsional deflection, for lateral it's lateral deflection, for torque it's 1 radian, and for lateral rigidity it's 1 unit. So the definition is kind of same. Now we'll see the difference between torsional rigidity and lateral rigidity. It came in exam in December 2015. So the first we have to write definition, and next definitions we discussed it just now. So next we have to write the formulas. So KT, torsional rigidity, is defined is equal to T by theta, that is equal to GJ by L, and the unit is Newton meter per radian. And the formula for lateral rigidity is F by del and the unit is Newton per meter. And the application where torsional rigidity is considered and is of most use is the most important criteria is machine spindles, and similarly the application where lateral rigidity is of most importance is transmission shafts running at high speeds. So there is one question which has came in exam for two to three times, which is classification of keys and different type of keys. So keys are broadly classified into six types: sunk key, saddle key, tangent key, Kennedy key, round key, and taper pins and splines. I'll repeat it once again: sunk key, saddle key, tangent key, Kennedy key, round keys, taper pins and splines. So there are 6 different types of sunk keys, but 3 of them are very important, which is rectangular key. So it is rectangular and its width is 1/4 of the diameter of the shaft, and the height of key is 2/3 of the width, and the key has a taper of 1:100. And then there's square key, which is everything similar to the rectangular key, just that the height and width are same, which is 1/4 of the diameter. And the last is parallel key. It can be rectangular key or square key, but it is taperless. We will go and see another type. So these are the important ones. We'll go and see what are splines. So the splines are multiple keys which are integrated with the shaft. So these keys which we discussed before are separate keys which connect the shafts, the driving shaft and the driven shaft. But the splines are multiple keys which are integrated with the shaft. They prevent relative rotary motion, but they permit relative axial motion between the shaft and the hub. Moreover, they provide much higher torque than single key between the shaft and hub. The applications of splines are in automobile gearboxes and machine tool gearboxes. And there are 2 different types of splines, that is straight sided splines and involute splines. Now we will see the differentiation between keys and splines. This question came in exam in December 2015, so there are chances it might come again. It's everything we discussed before, just in a table format. So keys are used to secure rotating elements, gear, pulleys, sprockets, and they prevent the relative motion between the two. So, and splines are multiple keys integrated with the shaft. Keys prevent rotatory as well as axial motion, but splines prevent relative motion but permit axial motion. And last is this: splines produce higher torque transmitting capacity. So splines have higher torque transmitting capacity and keys have low torque transmitting capacity. So these are the 3 points of difference between keys and splines. So we will see another topic now, which is couplings. Coupling is a mechanical element used to connect two shafts of the transmission system, and they are located as near as possible to the bearings to minimize the deflection. So there are two types of couplings we are going to see. One is rigid coupling and another is flexible coupling. Rigid coupling is used only for the aligned shaft, and flexible couplings are used for the misaligned shafts. So we will see how couplings are classified. So couplings are, one is rigid and another is flexible. Rigid is, there are three types in rigid: muff or sleeve couplings. Another is split muff or clamp coupling. Split muff or clamp coupling. And the third one is rigid flange coupling. Rigid flange coupling. And the flexible coupling also has three types. One is bushed pin type flexible coupling. Bushed pin type flexible coupling. Another is Oldham coupling. Oldham coupling. And the last one is universal coupling. Okay, so now we'll see where they are used. So muff or sleeve coupling is used for line shaft. Even split muff and clamp coupling is used for line shaft. And rigid flange coupling is used for connecting two perfectly aligned shafts. Two perfectly and then bushed pin type coupling is used for shafts with small angular or linear misalignment. Small angular or linear alignment. Oldham coupling is used for connecting two eccentric shafts. Two eccentric shafts. And universal coupling is used for connecting two shafts with angle in them. So we'll see it once again, we'll revise it. So coupling, two types, rigid and flexible. In rigid there are three types: muff or sleeve coupling, split muff or clamp coupling, and third one is rigid flange coupling. In flexible there are three types: bushed pin type flexible coupling, Oldham coupling, and universal coupling. Muffed or sleeve coupling or split muff or clamp coupling is used for line shaft, and rigid flange coupling is used for two perfectly aligned shaft. Bushed pin type coupling is used for small linear or angular misalignment. Oldham is used for two eccentric shafts, and universal is used for like two shafts with angles between them. Let us now see the difference between rigid coupling and flexible coupling. So these are the comparison parameters: the purpose, alignment, shocks and vibrations, cost, and examples. So purpose of rigid couplings is to connect two shafts which are perfectly aligned, and flexible couplings are used to connect two shafts having small misalignment. In rigid couplings, there cannot be any misalignment between the shafts, but in flexible couplings, small angular or lateral misalignment is okay. Shocks and vibrations. So rigid couplings cannot absorb shocks and vibrations, but flexible couplings can absorb shocks and vibrations. The cost of rigid couplings is not much, they are less expensive, but the cost of flexible couplings is very high, they are more expensive than the rigid couplings. The examples of rigid couplings we have already seen: muff, split muff, and rigid flange. For flexible couplings is push pin type coupling, Oldham coupling, and universal coupling. So we are done here with the second unit. We will go and see the first unit now. We will now see the first important question in unit 1, which has came in exam for 3 times in August 14 Insem, in December 16 and May 17. And the question is factor of safety. So factor of safety is defined as the ratio of material strength to the working or allowable strength. This is how we write the factor safety: material strength divided upon working or allowable stress. So there are 3 cases: factor of safety for static loading of ductile material, factor of safety for static loading of brittle material, and factor of safety for fatigue loading. So we'll see it one by one. For factor of safety of static loading of ductile material, yield strength is considered instead of material strength. So the formula changes to yield strength upon working or allowable strength or allowable stress. Factor of safety for static loading of brittle material, in that material strength is replaced by ultimate strength. So its formula becomes ultimate strength upon working or allowable stress. And for fatigue loading, endurance limit is used instead of material strength. So its formula becomes endurance limit upon working or allowable stress. Now, what is exactly factor of safety? Factor of safety is actually to ensure the safety of system against certain uncertainties, because while designing any mechanical system, there are always some uncertainties. So to avoid them, we have defined something called factor of safety. Next, we are going to see factors to be considered while selecting factor of safety. So there are 2 things. If there's higher factor of safety, the failure of probability would be less, but the cost of the material would be higher because of the dimensions. And if you choose lower factor of safety, the failure probability would be high, but the cost would be low. But if there's failure, then it's of no point, because everything will just fail. So we have to consider some factors while selecting factor of safety. So these are the 8 factors. First, degree of uncertainty about loading, degree of uncertainty about material strength, uncertainties related to applying loads to material strength, consequences of failure on human safety, consequences of failure on economics, extent of economic loss in case of failure, cost of providing a large factor of safety, and recommendations of standards and codes. First is uncertainties in degree of uncertainty about loading, degree of uncertainty about material strength. Third is uncertainties relating to applying loads to material strength. Fourth is consequences of failure on human safety. Fifth is consequences of failure on economics. Sixth is extent of economic loss in case of failure. Seventh, cost of providing large FOS. And eighth is recommendations of standards and codes. Next, when we see the design of quarter joint, there's one very important question which was asked before in the Insem exam as well. That is, why lower factor of safety is considered while designing quarter? So socket, quarter and spigot are made of plain carbon steel or alloy steel. Many of times the quarter is made of weaker material as compared to the socket and spigot, or has lower factor of safety because the cost of quarter is less as compared to socket and spigot. And if there is a failure, quarter should fail first instead of socket or spigot. That is why there is lower factor of safety considered for designing of quarter. Next we have, and this is I think the last question from this unit. This video is going to be very short because I was going to cover only theory, and this is the theory, total entire theory, which is important from both the units. The next part left is the numerical, which I'm not going to include in the video. So these are the last definitions. One is lever. Lever is a rigid rod or bar pivoted at a point called fulcrum, and it is used to overcome a load by the application of small effort, and it is used to facilitate the application of efforts in the desired direction. So now the definition of effort arm and load arm. In a lever, perpendicular distances of the effort and load from the fulcrum are known as the effort arm and the load arm. So one arm over here is effort and another is load. And now last definition, leverage and mechanical advantage. So leverage is the ratio of effort arm to load arm, and mechanical advantage is the ratio of load to effort. So this was it in today's video. Thanks to everyone for watching. I've not included numericals because it would have taken a lot of time to explain, so I just thought to cover theory. If you cover this only, this is the entire theory from both the units, it would be very useful. Thank you for watching the video. Please like, share and subscribe. See you guys in the next video. Bye bye.